Okay, let's continue. So the previous three parameters is quite commonly confused if you do not understand the concept or do not understand how to distinguish that. They'll become very confusing in the reference. And the following two parameters is relatively easy to understand. That transmissivity is the rate at which the ground flow horizontally through an aquifer, and transmissivity is the property of the aquifer system. It's not a property of the material. So from the previous part, although we do not emphasize, or maybe later we can see that hydraulic conductivity or intrinsic permeability is mainly based on the specific material. For example, commonly we use in like the gravels, sand, silt, clay to describing how high the hydraulic conductivity of the material. But the transmissivity is not for specific materials, it's for the aquifer property, because the transmissivity is obtained from the pumping test. And pumping test, commonly we open the screen in the intervals, and we don't care about exactly what kind of materials between that intervals. So we just directly using the pumping test to gather the waters to decline the water levels. So how we obtain the property, we define as the transmissivities. So that's a kind of equivalent concept. We just obtain the overall the property of that aquifer system. We are not exactly for specific material. So we mentioned that the aquifer properties. And another, it emphasizes the horizontal movement, because when we're doing a pumping test, we assume that the water is flow horizontally, do not have the vertical components. Although it's also ideal cases. If we do the pumping test in like real hydrogeological systems, so we see in the last slides, last lectures, they are arbitrary materials or they are quite heterogeneous systems. So they are not able to have only the horizontal movement. But for the ideal cases, if we have the fully penetrated behaviors, we were able to gather only horizontal flow patterns. So commonly we can say that we, under the assumption of the horizontal movement, we were able to use in the pumping test to quantify the transmissivity using the tight solution like that. And hydraulic diffusivity is a measure of the capacity of the subsurface or energies to be diffused or to allow something to pass by diffusion. Although this diffusion is not exactly what we know the hydraulic diffusivities, but they are describing the diffusion behaviors for the normal conditions. And hydraulic diffusivity is the combination for the two parameters in ground hydrology. We combine them together, the hydraulic conductivity and specific storage together, or the transmissivity and storativity together to form this hydraulic diffusivity. And for ground hydrology, commonly we do not use in this terminology or we do not use in this symbol because it combines two different kinds of the property together. But for some of the conditions like analytical solutions, they try to combine these two parameters together to simplify your equation. And then you will only have one parameter or one unknown left. And then your equation will be more simplified for some illustrations. And as I know that for the tectonic system or for some of the earth science system, they commonly using the hydraulic diffusivity to do the calculations. Because the equation will be more easier, they just need one parameter for the settings. But honestly speaking, this parameter is not able to directly obtained. Commonly, we assess is the T and S, or using the K values. We are not able to directly measure the D values, although we can use in some, yes, I think still able because you can derive your equations and using the observation to inverse the D values. But they are not very commonly used for the ground hydrologist. And let's take a look at the ground flow equation here. This is the ground flow equations we commonly use. I do not emphasize how to derive that in this semester. We have the partial differential equations. We have the hydraulic head values, and they vary with the spatial domain x, y, z. So this is a 3D system. And we have sink and source term, and we have another the time varies with the the time varies properties. And in this equation, we have two parameters. One is the K values, hydraulic conductivity. Another is the SS value, it's a specific storage. We're using these two parameters to describing the ground flow behaviors. So in this equation, you can see that it's very easy, only two parameters. Okay, so as I mentioned, we do not have porosity inside. We only have K and SS, or T and S. Later we have that. And here you need to understand that Kx, Ky, Kz, that means that they are directions. The subscript means they are directions. It illustrates that K in the X directions, K in the Y direction, and K in the Z direction. Okay, and these terms describing the spatial distributions. Okay, so this is the vary in the X direction, vary in the Y direction, and vary in the Z direction. They are spatial variations. But this one, Kx, is in the elements. So the concept is, like I mentioned, when we have IEV values, IEV volumes, in this IEV, we have the Kx, Ky, and Kz. But in these elements, they only have one Kx, Ky, and Kz. Okay, but in another elements, they will have another Kx, Ky, and Kz. It can vary. So the Kx, Ky, and Kz, then that means in the other IEV systems, they are the same. And also the SS value will be the same. Okay, we mentioned that in the IEV, they represent the same property of the materials. Okay, but you can also imagine that when we do the simulations, we have a lot of grid or meshes. So each of the mesh or elements, they have the same Kx, Ky, and Kz and SS values. But the different elements, they can have different values. So they become heterogeneous system. Okay, so numerical model will be able to let you set up different parameters in the spatial domain. So this partial means that they can vary in the different locations. And you will be able to integrate them together to be one of the domain for your simulations or your assessment. Okay, and this Q is the source and sink term. And be careful for this term because for source and sink, you might imagine like we might using the pumping quantities or the recharge quantity. That can be pump or recharge. But when you use the pump or recharge, you might imagine that could be the volume per time. But it is not, so be careful for the unit. It is the volume source per unit volumes, so they divide by the volume. So the unit will be, if you eliminate these two, they become the 1 over time. So be careful for the unit when you would like to use that, their equations. And we can also change these kind of equations to be another form. So if we assume that S value is the constant, it do not vary. And we can also divide by the total for the SS value, they become like this. And we can assume that if Kx, Ky, Kz is the same, they do not have different directions. Kx, Ky, Kz later we will mention about it. That means the isotropic properties. So we can assume that if we define K divided by SS is the constants, they equal to the T divided by S, that's the D values. So D here is the hydraulic diffusivity, as I mentioned previously. So in this equation, you can see that that's the diffusion equations. We only have one parameters, D values. Although they could be dx, dy, and dz, but if they are isotropic, you can take them out. They become just one D value. So you can simplify your equation to be only one parameter, only one unknown. Not unknown, one of the parameters, okay. And you will be able to solve the equations more easier. And if you're using a TS system, they become like this. You can substitute T and S to replace the K and SS, so they become T and S. And this kind of equations using for the pumping test or test solutions. And because we know T equal to KB and S equal to SSB, so you can input that, you can see that the B value is eliminated, so they become like the same D values. Okay. And although they can write down like this kind of format, but in a tight solution, we do not have the Z directions. we only have horizontal movement, so we have TS, TY, and S values for the test solutions because we only assess the horizontal movement. So how to do the management of the permeability of or the hydroconductivity? This part will be mainly taught by Dr. Chen, so I will quickly just review some of the concept. Commonly, we use in the Darcy's law to do this kind of work. And Darcy's law is based on the original experiment we call the Darcy experiment. And Darcy experiments like this kind of systems. We put the core samples in this kind of systems, and then let the water flow through one cross section to another cross sections. We measure the head values, and we measure the distance, and we measure how much water is outflowed. We will be able to using the equations, the Darcy equation, to derive the K values. And this kind of system means that we need to let the system reach the steady state conditions. Steady state means that the outflow equal to the inflow. Okay, so remember that when we're talking about steady state, it means the outflow equal to inflow. So we do not have the storage effect. Storage is the kind of the lag concept. For example, you have 1 unit flow in, you have 1 unit flow out. That means you just directly go through, do not have the changes. Although they are pushed, the water is inside and push the water out, not exactly the particle movement. So you have the same unit in and out, so they become like a steady state. But if you put 10, but they just have the 9 outflow, they have 1 left in the systems, and then the 1 we call the storage. Okay, and it could be inverse. You put 9 and they become 10 out, and they have 1 left. It's the -1 left. They become decrease of the storage. Okay, although it's not like this, but when we talk, the storage is the kind of behavior like this. So if you would like to do this kind of assessment, you need to remember that the system needs to reach the steady state conditions. So your inflow equal to outflow, and then you'll be able to use in the Darcy's law to derive the equations. And Darcy's law, we mentioned a lot of time in the last semester. We're using the velocity or using the volumes. If we're using velocity, then minus Ki, or using the volumes, minus Kia. So you cross the cross sections for this area, and you will be able to get the total volumes. And for the experiment, we only able to measure the volumes. Commonly, we measure the volumes, although we can measure velocity, but the velocity is quite depends on the shape. For example, if we have the channels, this is the channel systems. And your velocity will become like this. In the central channel centers, there will be high velocity, but in the boundary, there will be relatively less velocity. So how to measure the velocity sometimes is not easy. But for measure the volume, it's more relatively easier. So commonly, we measure the volumes. We let the system can have the outflow, to let the system have the continuous flow in and continuous flow out, reach the steady state, and then we'll be able to assess the volumes. And using the Q minus equal to the Kia. I is the hydraulic gradients. Height differences divided by the length differences. So they imply the unit length, how much the energy decline. Okay, so the hydraulic gradient like that. And cross-section you can measure, then you are able to measure the K values. And for the common sense, you need to understand that gravel around 10 to minus 3, sand 10 to minus 5, silt 10 to minus 7, 6 and 7, and clay commonly can be 10 to minus 9 or 10 meter per second. So this is very important part for you to memorize. And there'll be some reference. I think we quickly just let you review that. So you can see that the K value have different unit. They might have Darcy, cm square, cm per second, meter per second, or the others. But honestly speaking, they are the same concept, but they're using a different unit. And this is intrinsic permeability, and this is another Darcy permeability. Although they are exchangeable, so that's for your reference. And aquifer system, how we call the aquifer is good or not, is mainly for the water resources issue, so for your reference. And porosity, conductivity, hydraulic conductivity, also for your reference. So we emphasize that clay have the high porosity, but have very less effective porosity, and then very less hydraulic conductivity. So this is a very important property for clay. And the method to estimate the hydraulic conductivity, we mentioned that could be separated to 3 kinds of the methods. One of that is laboratory methods. We call the constant head or falling head. And in our lab, in the laboratory, Person's lab have the falling head test. So we will go to the lab to do the falling head test. Okay, we'll let you operate how to do the falling head test and then doing some of regular calculations. And in situ test, we commonly have the pumping test and slug test. And for the pumping test, we will go to the our campus. Just let me know that we can go to our campus. We have the well site. We can do the pumping test there. And I'll provide you the data set to inverse to calculate the hydraulic conductivity and or transmissivity. Try to do the operation for the pumping test. Okay, that's the important part. And slug test is differences. So there'll be many taught by Dr. Chen. And empirical methods, we're using like a pore scale, pore size, or soil textures to do the assessment. Okay, so this part I skipped. So laboratory methods, we can, following this kind of the parameter, we're able to do the calculation for the K values. Empirical methods we mentioned previously, and most commonly used is the common Bayer equations, include the particle size and also the concept. So this part is we talk that hydraulic conductivity is a property of the solid and fluid together. So this part is represent the fluid part. So they have the fluid density and fluid viscosity. So this is the fluid phases, and this is the solid phases. So in the following, we have the intrinsic permeability definitions following this kind of concept, or this is borrowed from intrinsic permeability. Okay. And for the other characteristic of the K, we have the heterogeneous and anisotropic properties. As we see in the last lectures, the hydrological properties or hydrological distribution is not, as we imagine, so uniform. They are quite heterogeneous. And even in these kind of systems, although you can see that, they are the same material, they are the same materials, they are the similar materials. But when you go into the deeper, or when you take the core sample, for example, even they are look quite uniform. You take the core sample to do the experiment in the lab, you will find that their K values could vary, maybe 1 order differences. Okay. So one of the concepts is that when the hydraulic properties is within 1 order, commonly we will say that they are similar, although they can have several times differences. But if they are in the same order, we will say they were similar because they have larger uncertainties. And even using the same material, like I mentioned, the same material to do the experiments, they can have larger variations. And yeah, this one, if they are close, maybe the property is quite similar. But when you have the longer distance, they will change because the deposit environment will change. Like we can know that for the alluvial fan area, commonly larger grain size will deposit in the proximal fan, and then middles, and then to the distal fan, they become more fine-grained materials. Although they are the same edges or they are the same system to do the deposit, right? But their grain size distribution will be different. So your hydraulic property will be different. Okay. They are the same formations, but they are different property for the hydraulic conductivity. Okay, so be careful for this issue. So heterogeneous commonly exists in natural system, although for the small scale, maybe they are relatively similar. And anisotropic is also quite largely be observed because I mentioned, as we mentioned, the deposit environment like this kind of conditions if your particle have the shape, not the grain size, they might have a little different shape. They will have their preferential deposit directions. And then this kind of deposit behavior will let your flow behavior differences. For example, if your deposit is like the shell or the plain systems, if your particles is not a granular, they look like this. So you can imagine that the water flow in these two directions, the ability will be different. This one will be more difficult to flow through, but this one will be easier to flow through. So the K value here will be higher than these directions. So you will have the, we call it anisotropy properties. Kx and Ky will be different. Your Kx will be larger and Ky will be smaller. So we call this anisotropy properties for that. So commonly, that could be depend on your scale. When your scale is going to the small scale, commonly small scale like this area, maybe they are isotropic properties. But if your scale is relatively larger, you can see that they will include the different material. So later we will see that equivalent concept. This direction will be easier to have the flow, but this direction will be difficult to have the flow. So your Kx and Ky will be different. So they also depend on your scale. If your element, I mentioned IV, is different, so your result will be different. Or you construct a relatively larger scale for your models, or using a small scale for your models. Your element is different. Element is more or element is larger, then your property will be different. And we're using this one to illustrate the heterogeneous and anisotropic. So if they, we're talking about heterogeneous means they are the different locations. And isotropic means, or isotropic or anisotropic, we take a look at the same locations, okay? So the same locations, if their X and Y is the same, we will call this the isotropic. And different locations, if they are the same, we will call this the homogeneous. So even like these kind of systems, they are the same directions. So this is the isotropic properties. But this location, these two locations have the different properties, so we will call the heterogeneous. And like this, S and Y have difference, so we'll call it anisotropic. But these two locations have the same property, so we'll call this the homogeneous. So one of that take a look at the same location, and one of that take a look at the different locations. So we can go back to the equation concept. In the equations, in the differential equations, inside we have Kx, Ky, Kz. So they're describing the directions in that elements. One element, they have Kx, Ky, Kz. But for the partial, outside partials, that means different elements, you will have the different properties. So they become homogeneous or heterogeneous concept. Okay. So all of that can be connected together. You are easy to understand the concept. Yeah, and recent research, as I mentioned, that we go into the heterogeneous system and even anisotropy properties. Because maybe one of the reasons is that all of the isotropy and homogeneous system we already studied, we have investigated. So we need to create a new knowledge or create a new topic for the research part. So right now, researchers go into the heterogeneous system and anisotropic systems, and they become much complex. Okay, and the other reason could be that right now the computer power is much stronger, so we can using a complex model to do the simulations. In the past, we only able to do the very simplified simulation, but right now we can using complex. We have the supercomputers to do the calculations, so we are able to do the much complex assessment. So right now, I can see a lot of papers starting to do this kind of tensor systems. We have K, X, Ky, Kz. We can use the K tensors to do the assessment. In the past, we commonly using the Qx equal to minus Ki, like this, like the, okay, I wrote the Darcy equations, V equal to Ki, right? So this is the Darcy equations. But for the 3D system, if we consider more completely 3D system, they will have the component contribute from Y and Z direction. And in the Y direction, they also have another contributions. Z also have another's. So they become very complex. So what we talked in the previous case, KY, KZ, become like we call the principal direction. Principal direction is that when we have this kind of system, tensor systems, we can rotate our coordinate system. And you will be able to find in a specific systems, you will only have KS, KY, and KZ. And then we call that directions the principal direction, okay? But for really problems, like when we calculate, when we're doing the simulation for the like Joshua River Alluvia fan, we're using the NSEW to be our coordinate system, the vertical, right? The plane. So we are not exactly shifted to the principal direction, but we just assume the system can be separated to KS, KY, and KZ. But if we would like to more completely assess this kind of behavior, we should include the tensor. But for the sedimentary issues, right now still do not have these kinds of complex tensors. We were using KS, KY, KZ only. We're not using KSY, KYZ like that, complex. But for the rock fracture system, rock mechanics, right now they try to include more of this kind of tensor system. Okay, because the fracture system, they have the preferential flow paths, or they have the fracture orientations. They might have 2 set or 3 set of orientations for the joint or the plant. So they will be able to assess that kind of geometry. And we can use in equations to do the calculations. From the geometry of the fractures or the joint, we can calculate to these kind of K tensors. And then we were able to use in this tensor to describing the fracture system in the numerical simulation. Okay, so right now, more advanced technical will be focused on this. But honestly speaking, I have not joined this kind of complex system. I'm not as familiar with that. Maybe Professor Dong's lab will be more familiar with this kind of system, the tensor, okay? And for the principal directions, we commonly, we can separate them to be like this. So they will become only have KS, KY, and KZ, okay? And for the ground hydrology, we commonly separate, we commonly assume KS equal to KY and equal to the horizontal K, and they will be much larger than KZ or K vertical. And this depends on the parameter obtainable, because when we would like to obtain the K values, we commonly use in the pumping test. And when you do the pumping test, we assume that's the radial directions. Okay, cylindrical coordinate system. So the radials, we will assume they are homogeneous. We use the ideal case. So we are not able to separate KS and KY because they are the same in the horizontal directions. So this assumption is based on our TICE solution. Although we are able to calculate KS, KY, and KZ, but they are not easy to obtain for the in situ test, okay? You are able to do this kind of work if you have more observations for the pumping test. You might be able to calculate the directions. But honestly speaking, they are not easy because in the real situation, they are heterogeneous. So even you have like a geometry, like you have this direction, we assume they might be the same. 1 pumping wells and 2 observations nearby in the same line. But when you do the test, your K values, this direction and this direction still be different. Okay, so they are not easy to get this kind of even anisotropy property. Yeah, but honestly speaking, because we mentioned that the K values or hydraulic properties itself embedded huge uncertainty. So we are not care about the tiny differences or the small differences. We just have approximately the quantities, and then we can use that to quantify like how much water volume we obtain. Okay, that's for the groundwater resources or the most of the groundwater hydrologists. They have this kind of concept. uncertainty itself is much larger than the values Kx and Ky. Okay, like that. So you don't need to care about the tiniest differences. But for the vertical part, commonly you will assume the vertical will be relative dash K values. Because like the right-hand side, the structures, the quantum flow in this direction and this direction, commonly they need to penetrate the interface. So their Kz commonly will be less, 1 order or 2 order differences, or even 3 orders. Okay, but there will be another interesting issue is that for the tectonic assessment or for the fractal assessment, even like a geothermal system, we will say that the vertical K will be very large because they mention that the infiltrations to the deeper system is very quick. Like we can see in the fault systems, they found there will be a very deep signals from like maybe 10 kilometers, and they can observe on the surface. So they mention that the water is from the deeper 10 kilometers to the surface, and they are almost very short period of time, maybe several hours, they can reach that. But honestly speaking, if we're using the quantum hydrologist concept, they are not able to have this. And they were using the diffusivity to do the quantifications. So if we do these kind of papers, commonly we will feel that the D value, they will inverse the D values. The quantity is very abnormal. It's out of our expectations. They do not match the concept for quantum hydrology. Yeah, but they still publish because they do not have much of the background for that kind of concept. And we have equivalent K values. That means if you have a layer system, like a traditional layer system, if we assess the K, if we assess the water flow parallel to the layer or perpendicular to the layers, you will gather the different velocity or different equivalent K values. So the concept is that if we put this kind of material in your Darcy's experiment, we don't think, as I mentioned, we don't care about exactly what the materials between that space. We just put the material inside and we can have flow in and flow out. So what we got will be the equivalent K for the whole systems. So you can put this kind of layer system in your experiment and you'll get the equivalent K. And you can also put another perpendicular to your flow directions layer system in your system, and then you can have the flow in and flow out. You can assess the K values. So these K values we call this equivalent K. They look like a kind of average, okay, a kind of average, but the average will be differences like this kind of situations parallel to your flow direction, your formation directions. You will have the geometric mean concept. So your K, equivalent K multiplied your thickness, total thickness will be the summation for each of the layer systems, okay? So they become like a kind of geometric mean concept. And if we use in the perpendicular directions, they will become like a horizontal mean, harmonic mean. That means that you take this one and take this one, you should switch these two. So your length divided by your equivalent K will be the summation for each of the lengths divided by the K values. Okay, so this is a kind of harmonic mean concept. And if we using the real values due to the assessments, you will got a relative low K values for this kind of structure and high K value for that kind of structures. The concept will be that, as I mentioned, we would like to assess the K values. We need to let the system reach the steady state condition. And when it reaches the steady state, that means your Q in and Q out will be the same. Okay. So if you have the materials very low K values, it will mainly control your flow velocity. So it will be very difficult to penetrate your whole system. Okay. So you will got the relative low K values. And if you have these kind of structures, you have low K value here, but you might have high K value here. And your water flow, these directions, when they touch this surface, most of the water will go into this area. try to find the easy way to flow through. So your most of the water will flow to the high K, so your got the equivalent K will be relative higher or approach to your high K formation. Although they still have some small penetrate to this area, but most of the water go to the high K values. They depend on how large K difference is. For example, if you have 1 order or 2 order differences, maybe most of the waters, or maybe 90% of the water, 90 more, go to the high K values. But if your K values have just slightly differences, they will be more uniform like that. Okay, so this kind of concept is also very important. As I mentioned, when we do the pumping test, commonly like this, so we got the intervals. So we got the equivalent equivalent T values. We have transmissivity, but that's the equivalent for the aquifer system. And if you have the different kind of material, you will be able to calculate equivalent quantity. But honestly speaking, it's also not easy because we are not able to have precisely the K for different depths. But you are able to imagine that if you have the gravels in that intervals, your gravel will be the dominant. You become like got the high K value or high T value. Okay. And intrinsic permeability is the empirical relation for the hydraulic conductivities. So we write down like this format. Hydraulic conductivity can be separated to the free part and solid part. The free part we use in the density of the water and also the viscosity of the waters. And the solid part we don't know because they are combined, integrated parameters. So we give it a parameter called intrinsic permeabilities. Okay. So we separate the free part and solid part to combine with the hydraulic conductivity. So the small k is the shape factors. They affected by the particle size, particles shape, distribution of the particles, pore spaces, shape of the pore spaces, etc. So they are not easy to be quantified. So we just give it empirical parameters. So that means that for a specific soil, the k, small k, is the constants. And we may have different Ki for the various fluid inside it. Okay, so we got this kind of concept. So when you have different kind of fluid, you have different kind of the viscosity, different kind of the density, and they will have the same K values. So you'll be able to calculate the hydraulic conductivity for that kind of material. Okay, so that's the concept. So in Professor Dong's lab or in some of the mechanical experiments, they might using the airs to do the experiment. If your K value is very small, they are not easy to use in the traditional water for the experiment. So you can use in the airs to input inside, and you can got the K. You can use in the system to obtain your intrinsic permeabilities, and then you will be able to replace the parameter to obtain your hydraulic conductivity of the water. Okay, so this is a concept for that. And transmissivity, as we mentioned, is describing also the similar concept, but we have the thickness concept inside. So the pumping test is to estimate the T values, not the K values. So for the aquifer thickness or open screen thickness, K values are calculated by T equal to Kb. Although most of the conditions or most of the situation we do in the numerical assessment, we using the K values, not using the T values. But you should know that for the reality, we commonly using the T value for the reality assessment. But in the numerical models, we are not able to using T values. Or if we using the T value, we should using the aquifer system to construct the whole numerical system, not using the materials for the assessment. And then you'll be able to put the T values. But the T values, it become like the like an equivalent concept. So overall equivalent concept, how can it be using for the assessment is also not easy. So commonly we still go back to using the K values instead of the T values for the assessment. Okay, and the T values have the unit of the length squared per time. So also need to be careful for that because we have T equal to Kb. So if you memorize these equations, you will know meter per second, and then divide by the meters. So they become, multiply the meters, so they become the meter square divided by second. Okay. Yeah, so the T values is like this, and they are obtained from the pumping test. And pumping test, I think we will talk about that later in the quantum hydraulic, the well hydraulic system, to that you understand how to assess the T values from the pumping test. And following will be the water storage concept. And water storage is quite interesting issues. We also mentioned in the last semester that the storage coefficients itself represent the deformation part. Although in quantum hydrology, we ignore the deformations. We just mentioned they are just the waters in or out. But for the storage properties, it represents the deformations. So we commonly using two kind of concepts together, like the matrix compressibility and the water's compressibility to describing the specific storage. So in the field of the hydrogeology, storage properties are physical properties that characterize the capacity of an aquifer to release the groundwaters. And we have three terms commonly used: storativity, specific storage, and specific yield. Storativity is the more general term, although we talking about the pumping test, we're using the T and S values. So the T is the transmissivity, and S value will be the storativity. Okay, so these two will be the aquifer properties that we can obtain in the pumping test. And specific storage and specific yields is using for the different aquifer system. Like a specific storage, we mentioned there will be the property for the confined aquifer. And specific yield is the unconfined aquifer property. And all of the storage coefficients describing the same or the similar concept is how much water we can obtain from unit current of the head. Okay, so unit current of the head, how much water we're going to obtain is the storage concept. Although the definition is a little differences for these several parameters, because some of that are using like a kind of average concept, and some that are using the advanced I mentioned, like specific storage, using the mechanical concept. They have the deformations inside, so they have a little differences. So in a unconfined aquifers, the main source of the water is the drainage of the water from pores as the water table decline in the response to the waters. So if we talk this kind of the system, that's the connect to the atmosphere. So this is the water table we mentioned that. So this is an unconfined aquifer system. When the water level decline, it will be very easy to imagine that this is the pore spaces. So the waters released from the pore spaces, we take the waters. This is the concept. Okay. So this is very dirty imaginations. There are no problems for this. But for the confined aquifers, they will be difficult to explain. This is a confined unit. In this confined unit, and the water here is fully saturated. And the imagination levels will be here, the pressure levels. And after we take the waters, the pressure level decline. Okay? So the question will be, originally these volumes, they are fully saturated. And you take the water out. But they're still fully saturated in these columns. So before it's a fully saturated at the red column. After it's the fully saturated at the red columns. So how you can cut the waters? Okay, that's the problems. Do you know what I'm talking? This part? Fully saturated in these spaces before take waters. And after take waters, they are fully saturated. They look like the same. But you can take extra waters here. So where does the water come from? Okay, so that's the main issues we'd like to discussing for the confined aquifer system. So for the comparable unit crime of the hydraulic head, on confined aquifer release much more water from, they do not explain that. They release much more waters. They're describing the water, okay. But they do not explain the mechanism. Okay, this one describing that we decline this small, we can gather this amount, but we need to decline much larger to gather the same amount. Okay, but they do not describing why they can gather extra waters here. So researchers using two mechanisms to describing these behaviors. The first is that the matrix be compressed. Okay, so originally they might have 100 volumes, but after you take water, they become like maybe 95. Okay, they compress 5, so you can have extra waters be take out. And another part is originally the water amount in the pore spaces could be 100s, but after you take waters, they become like 90s. 10 be take out, but how can they be take out still fully saturated? So they will expand. The volume will change. Not the volume changes, the volume is the same, but the density changes. Okay. So we use in two kind of mechanism. One is that matrix be compressed. Another is water expand. So when matrix be compressed, then you will have extra waters be take out. And water expand, and you can have extra waters be take out. Okay. So we use in these two mechanisms to describing why confined aquifer can release water. The storativity of the aquifer is defined as the volume of the water that the aquifer release from or take into storage per unit surface area of the aquifer. Okay. So the storativity is like this. They have the unit decline of the head, how much water can release, but they also divide by the unit area. So they look like the unit area, how much water you can obtain. So they become like a kind of average. And for the confined aquifers, the value for the storativity range from 10 to minus 3 to 10 to minus 5. So be careful for this quantity, because if you are using the different values, or if you do not have this common sense, you will get the wrong result. Confined aquifers, as I mentioned, they are compressibility of the matrix and expand of the waters. So the amount of the release ability is very few. Okay, so you can memorize this. And then the few value means you will get the relative less storage coefficient. Okay, and in the unconfined system, they relate to the porosity, your pore spaces. So the quantity for the released water will be relatively large amount. So you're easy to obtain the larger storativity for the unconfined aquifer. Okay, because we already mentioned that before, I do not repeat too much. Just so that you understand that if we have the SS value, specific storage, we divide one more is for the unit aquifer thickness. Okay, that means every thickness, every unit of the thickness, how much water we can take out. It can release the waters. Okay, the same. The other is the same. So we have an extra part for this. So unit thickness, unit area, how large water can obtain, we define as a specific storage. Seems the time approach. So maybe let me take a look. Still several slices. Maybe we talking about that, or maybe we just finish this part. Okay. So for the confined aquifer system, we're using two mechanisms, as I mentioned, that the storage coming from compression of the granular matrix and also the expansion of the waters. So we write down the equation like this. This is the matrix compressibilities. This is the water compressibility. So we combine these two, but the waters only occupy in the pore spaces. We multiply porosity here. Okay. And then this is the volume of the water, and we need to multiply the gamma W or low G values. And then we got the total amount of the water for the water quantities for this. So the specific storage we define is equal to this equation. So matrix and water expansion. So you can imagine that in the quantum hydrology, we do not consider the deformations. But in reality, they should be included inside. So that's also a reason I talk a lot of time that if you would like to study more completely for the quantum hydrology, you should use in the hydromechanical parameter, hydromechanical equations. you cannot ignore the deformations. You should include that inside, and then you can get more completely solutions for your assessment. Okay, yeah, like this. And you can know that the compressibility of the water is very few, the quantity is very less, 10 to minus 10. So that means they are able to release only very few quantity of the waters. So that's the reason I mentioned the specific storage or the confined system. They are only able to provide very few quantity of the water for that. But is that match the reality? Maybe no. Okay. This is from theoretical, but for the reality, when you do the pumping, do the pumping in the in situ field, shallow depths and deeper depths, when you do the pumping, you commonly just pump a lot of waters. And you can see they have the decline, but maybe not so large. As I mentioned, theoretically you pump in the unconfined aquifer, you can see less decline of the head, and in deeper confined system, you will see large decline of the head. But for reality, maybe not. Okay, they have other inferences, not only this kind of mechanism. So there's different issues here. Okay, I think I'll stop here. Any questions about today's talk? Okay.
I have a small question for the chemical and hydraulic properties.
Mm-hmm.
Because to obtain this value, you may need the drilling. I'm curious whether the sample is turned during the drilling or because of the unloading effects. So the soil structure may be changed. So whether it's quite challenging to obtain from the samples.
Yeah, sure. If you take the core sample back to the lab, commonly the quantity will be affected. Yeah, one of that is they release the stress. They will have the different behaviors because they become expand or become more, loose materials. So the K value will be different. But another is that we mentioned the scale effect. When you go back, you take the core sample, go back to the lab, what you obtain is the small scale K values. Honestly speaking, they are not able to represent the real or the in situ K values. Because the scale is larger differences, they are not able to directly use. Although we commonly have the K value still input, but if you do not do the in situ calibrations, that K value is not a reality for the usage. And as I mentioned, that the K value commonly, if they are within the one order of magnitude differences, we will say they are similar. So even expand a little bit, maybe they are not largely affected for the quantity. They're affected, but maybe not so larger affected. Or you can just tell them back to have the constraint or using the confined pressures to let them go back to the loading conditions. That could be another possibility. But you need to use in a 3 triangle test. Yeah, that will be much complex for this issue. Like this, okay. Others? Okay, if no, we stop here. Thank you very much.